In the previous video, I talked about AdaGrad optimizer. So AdaGrad is basically, it introduced adaptive learning rates for gradient descent. So in this video, we'll talk about RMSProp, which is a modification or improvement over AdaGrad. But I highly suggest please go through the AdaGrad video first. I am just giving a quick recap here. So we were using one square gradient accumulator, this RT. This is a square gradient accumulator. This is a vector. So for this gradient is also a vector, right? Next to this delta, this is a hyperparameter for stability. So earlier in the normal gradient descent, we just had this alpha as a gradient, as a learning rate. But here we are using alpha divided by this thing, square root of RT plus 1 plus this delta. Forget about this delta for now. This is just a stabilization factor so that we don't get divide by 0 error. So as this RT plus 1 increases, this whole thing will decrease for that particular weight, right? If this RT plus 1, where the value is less in this RT plus 1, this term will increase. So for the sparse features, we'll have larger step sizes. For frequent features, we'll have smaller step size or learning rate. So that is the idea behind AdaGrad. So that is the adaptive learning rate. But we saw one minor drawback of AdaGrad. So we had this problem, aggressive learning rate decay. So when this RT plus 1 or RT, this term square gradient accumulator, this keeps getting increasing, right? So when it is increasing, this term will decrease for that particular weight, right? So when RT entries keeps increasing, effective learning rate for those weights will become like close to 0 or minimal. So that is the problem. So if the learning rate for those weights becomes very negligible, so those weights will not learn. So what happens is accumulate square gradients forever, right, in this square gradient accumulator. So learning rate keeps shrinking, and that's why training slows down or stops for few weight parameters. That is the aggressive learning rate decay problem we'll try to solve here in RMSProp. So RMSProp is basically one improvement over AdaGrad. So what we want? We want adaptive learning rate. Of course, that AdaGrad has already introduced. So this instead of one alpha as a learning rate, we are using this vector. So right, for different weight parameters, we are having different weight, different learning rates. But without this learning rate decay problem that AdaGrad had. So that we are trying to solve here. Plus 1. So if instead of increasing this RT forever, can we limit this RT value? So that is our motivation here. So this RT, if this increases, this term will reduce, right? So that's what we don't want for all the variables. So we need to limit this RT value. And one solution here is using convex combination for RT. Now, what is convex combination? If you know this, very good, but I am just giving one quick intuition. So convex combination for two variable is, let's say this is one A and this is one B. So this Z, so this is a row A plus 1 minus row B. So row is one value between 0 and 1. So this, if this is Z is this is called convex combination. So Z value will always be between A and B. So Z is always between minimum of AB and maximum of AB, some value between these two. So this is called convex combination of two values, two variables. So here for RT also we will use convex combination. So row times past plus 1 minus row times present. So this is basically considering how much past memory will preserve, and this is defining how much will adapt the present values. So now this is the improved formulation, and this is for RMSProp. This part is remaining same. We have this vector adaptive learning rates. Just how we are calculating RT or RT plus 1, that is changing here. So here we are using a convex combination representation of RT. So earlier what we are doing is RT plus 1 was RT plus this squared gradient, right? So this is squared gradient. So we are just always increasing this RT values. So we are taking the squared gradient and we are updating it. We just adding. So this is kind of was cumulative sum. But instead of that, we are using rho RT plus 1 minus rho the squared gradient. So this is basically is between previous RT and current squared gradient. I am writing in this way. So we'll get a value between these two. So new RT plus 1 will be somewhere between these two. So let's say next time we might get Z values, gradient values here, square gradient value here, or also we can get here, right? So our new RT values will be between this range or between this range. So we are kind of trying to limit the RT values, and that is the main thing. So rho here is how much past you remember, and 1 minus rho is defining how much you trust your current gradients. So one point is we are trying to limit the RT values. This is not getting increased every time. And then one thing is all gradients fade exponentially. So let's say this RT values, right? These RT values we are ignoring. So the far ancient past we are trying to forget. So RMSProp has ability to forget all gradients, we saw, and it introduces memory decay. But this is not a problem. This is what we want. We don't want to remember the old past, right? Old RTs. So uses a moving average of squared gradients instead of a cumulative sum. So that's what we saw, right? So this is kind of a moving average we can call. So RMSProp remembers recent behavior, not ancient history. So recent gradients matter more than the old ones. So why this moving average helps? So RT remains limited, we saw. Old gradients fade away and learning rate doesn't vanish. So we get a stable long-term learning. So this forgetting the ancient past, so that is a feature. This is not a bug, and this is what is keeping the RMSProp learning alive. So the adaptive behavior that already was introduced in the AdaGrad optimizer, that is present here. So you see, this is the part. So sparse features, so the weights related to the sparse features, the larger step size or larger learning rates we are getting. Feature weights which are getting updated frequently will get smaller step size. So that is still there. That was already there in AdaGrad. It is still present in RMSProp. What new we have is balanced running across parameters. That is this part. This we are using convex combination. So each parameter learns at its own pace, but keeping the learning alive. We don't have this aggressive learning rate decay problem in RMSProp. So that is the improvement we see over AdaGrad.